let me start with okay, laser pointer. Okay, today I'm gonna present a special lecture, especially related to hydrogen storage. Please remind that previously I was talking about the hydrogen production technology. Today, I'm gonna start with hydrogen storage. Okay, okay, sorry. Okay, so this is the hydrogen economy. So to achieve the hydrogen economy, what we need to do is to produce hydrogen first, then how we can store mass quantities of hydrogen and how we can deliver the stored hydrogen in an economically feasible manner. That's the key thing. So today I will focus on the hydrogen storage technology here. Okay, let me first talk about, I discussed with, how we can categorize the hydrogen storage technology. We categorize the hydrogen storage technology like this. The first method is a physical hydrogen storage, and the second method is the materials-based hydrogen storage technology. If you see the physical hydrogen storage, the one of the most representative commercial technologies here is the compressed hydrogen storage and the liquefied hydrogen storage. And the material-based hydrogen storage technology, so we can use adsorbent. So I'm going to talk about methyl organic primer. And another technology for material-based hydrogen storage is the metal or complex hydride. And the third one is the organic hydride, mostly talking about the LOHC, liquid organic hydrogen carrier stocks. Actually belongs to this organic hydride-based hydrogen storage technology. And the last one is the inorganic hydride. The most representative example is ammonia. So let me first talk with the physical hydrogen storage. Actually, if you look at here, some other dotted line here. So what it means is, especially for adsorbent based hydrogen storage technology, also can belongs to the physical hydrogen storage. Okay. So what's the physical hydrogen storage technology? So if you look at this technology is actually based on the physical force, the physical the physical force. So if you look at this, the compressed gas means we pressurize hydrogen tank to store more and more hydrogen here. So the liquefied hydrogen technologies involve the cryogenic cooling. So we cool down to 20 Kelvin to make liquid hydrogen. So, as you can see here in the picture, if we take the liquefied hydrogen storage technology, the storage density can be much higher than that of compressed hydrogen storage. And the adsorbent-based hydrogen storage, the basic concept here is we use some of the materials here, and using the physical force between this adsorbent and the hydrogen can be, adsorbed at the surface of this material and stored. That's the thing. And for a material-based hydrogen storage technology, it is also called this a chemical hydrogen storage, which means it's the way that hydrogen stored is involved with the chemical bonding. So as you can see here, the metal hydride, the organic hydride, and inorganic hydride. I'm gonna talk about more detail later. So let me first more talking about the physical hydrogen storage. So this is the compressed hydrogen storage. Generally, we use the 700 bar pressurized hydrogen in a tank. So one of the most important thing for here is to optimize geometry and how we can store more and more hydrogen, and how we can make a safe tank for compressed hydrogen storage. And another thing is the liquefied hydrogen storage. And again, we cool down to 20 Kelvin, so negative 253 degrees Celsius, and to make a liquid hydrogen. So this is the real commercialized tank for pressurized hydrogen storage. This is used for hydrogen fuel cell electrical vehicle here. So the Hyundai Motors in Korea, so one of the famous motor company in the world, actually they take the compressed hydrogen storage for these types of hydrogen fuel cell vehicle. So this is all Koreans here. So you can ignore the if you look at this the red box here, that means it's the 700 bars of pressurized gas tank actually equipped inside this fuel cell vehicle. So 700 bar tank actually can contain about 5.6 kilograms of hydrogen. And if the driving range will be nearly 600 kilometers. And actually that Hyundai Motors actually developed this technology in 2013. And after 5 years, Hyundai renewed this fuel cell vehicle, and the model name is the Nexo. So Nexo vehicle actually used the hydrogen storage tank and can contain 6.3 kilograms of hydrogen. If you refill this and the refill hydrogen, the duration is only 5 minutes, and you can drive over 600 kilometers here. And so that's the picture for the hydrogen storage tank. And another very famous company, Toyota, actually the Toyota developed the Mirai, Toyota Mirai electrical vehicle shown here. And here is also they use the pressurized hydrogen storage tank here, and store about 5 kilograms of hydrogen under 700 bar. And the second generation, they also use that, and the hydrogen storage tank volume is a little bit extended. And the last example for pressurized hydrogen is the Honda Clarity. Honda Clarity also equipped the hydrogen storage tank with a 700 bar here. So they can store also 5.4 kilograms of hydrogen and drive about 400 kilometers. So if you look at the energy density of tank system for passenger car here, and the gravimetric energy storage density, if we take all metal construction, so that means these all tank material is the metal, then gravimetric energy storage density, hydrogen storage density is about 1.78%, right? And the type 4, this is the most advanced pressurized hydrogen storage tank that actually they used all composite materials here. So it's a very, very light materials, and the carbon based on the polymer liner and wrapped with the carbon fiber composite, and the gravimetric energy hydrogen storage density is increased from 1.78% to 5.7 based on Toyota Mirai. And for more hydrogen, for example, the 300 kilograms of hydrogen delivery, actually we use these types of very heavy materials here. This is tank, and that pressurized under 200 bar. So gas tube trailer, and the US company actually developed these types of 500 bars of pressurized gas tank, and you can take more. It's about 500 kilograms of hydrogen at one time. And the second method for physical hydrogen storage is the liquefied hydrogen storage. if you look at actually the hydrogen composition, and the molecular hydrogen exists in two isomeric forms here. So the nuclear spins is the parallel, then we call this ortho hydrogen. And the nuclear spin, the hydrogen and hydrogen, the proton spin is anti-parallel, then we call this a para-hydrogen. But interestingly, the gas state molecular hydrogen actually consists of 75% of ortho hydrogen and 25% of para-hydrogen. But if you look at this, the para-hydrogen can be transformed into ortho hydrogen, and the thermodynamic equilibrium, the delta H is 1.4 kilojoule per mole. If you cool down this hydrogen to make liquid hydrogen, then this composition can be changed here. So liquid molecular hydrogen, the para form is the major form. It's the over 99.7% of hydrogen will be exist as para form, and 0.21% will be exist in ortho hydrogen. So what could be the issue is when you cooling down, that means is 75-25% of this form will be transformed. So if you look at here, the liquid form is the mostly para form, which means is the also hydrogen will be transformed into para. That means is the ectothermic reaction can be happen, which means if you cool down, the also hydrogen will be transformed into para form with releasing heat. That means is you need more energy for cooling down. That's the one of the issue. So one of the R&D area for the liquefaction technology here is develop a relevant catalyst to release less amount of heat when these forms can be will be transit. So this is a real example. The BMW company actually developed the hydrogen 7 biofuel motor here. So they use liquid hydrogen, and it's about over 100 liters of liquid hydrogen, which means is you can store 8 kilograms of hydrogen. And the Ion Tiger fuel cell, the UAV means it's the unmanned aerial vehicle. It's a kind of drone, actually, which was developed by the US Naval Research Lab. This Ion Tiger drone actually used the liquid hydrogen inside here. And the Boeing, in the United States, the Boeing company, they developed the Phantom Eye unmanned air vehicle. It's a kind of big drone, and actually they use liquid hydrogen and the internal combustion engine to drive this Phantom Eye. And this liquefaction technology is much advantageous in terms of hydrogen storage compared with the compressed hydrogen. Remind that the compressed hydrogen just store only 300 kilograms of hydrogen on the 200 bar shown here, and the volume is very big. And in the case of liquefaction, liquefied hydrogen storage truck, so similar volume, you can store and deliver over 3,000 kilograms, 3,500 kilograms of hydrogen under only 1.3 bar. So you can store more hydrogen under nearly atmospheric pressure, which means you can store and deliver a large amount of hydrogen with a much higher safety level. And that picture actually shows you really big tank for storing liquefied hydrogen, which was actually developed, constructed by the NASA. NASA actually get this kind of a big tank for the rocket fuel. And this is a recent actually example. This is the bench. Daimler Group actually developed Gen hydrogen truck like this. and they actually refill the liquid hydrogen to drive this kind of truck. And we can also, store hydrogen using compression technologies in combined with the cryogenic liquefaction technology. This is called the cryo compressed hydrogen storage, which is still, again, this is a physical hydrogen storage. This is cryo compressed hydrogen storage tank, which was developed by BMW in 2011 of year. So that actually, the basic concept here is you store hydrogen under really, really low temperature and high pressure. So this is, you see the operating pressure is about 350 bar, and also you cool down this tank for storing more hydrogen. So CC means as a cryocompressed hydrogen. You see here is a 7.8 kilograms of hydrogen can be stored inside of this tank. And another examples for hydrogen storage, physical hydrogen storage, is we can use actual absorbent or adsorbent here. The one of the example is we can use the metal organic framework, which is called the MOP. The MOP use actually this kind of pores inside, and the surface area of this material is very, very high. So using the this kind of a large surface area and these pores, we can store hydrogen inside here under liquid nitrogen temperature of 77 Kelvin. Okay, that's the basic concept. But this is scientifically very interesting. But in terms of gravimetric hydrogen storage density, these technologies doesn't actually meet the commercial level of target for hydrogen storage. So nowadays, this technology is not actually commercialized. Yeah, that's the concept for a hydrogen storage tank equipped with the MOF, which was developed by Argonne National Laboratory. Okay, so I'm gonna skip it. But if you look at, so yeah, I was actually talking about the physical hydrogen storage, but let's see. The basic concept for the carbon neutrality based on hydrogen, that's the really concept. What is that is actually, if we get really, really cheap renewable electricity based on wind or solar or other stuffs, so we can store this renewable energy using water electrolysis to convert to produce hydrogen, which means we can store this renewable energy as a chemical form of hydrogen. Then this hydrogen will be transformed into the hydrogen utilization site. Then the question is how we can deliver this hydrogen into here. Can we use physical hydrogen storage for this purpose? No. So I'm gonna talking about that later, more detail. But so based on this concept, actually new technology will be needed. So this new technology can be the material-based hydrogen storage technology. So let me continue for why physical hydrogen storage and why we need new technology for this purpose. Okay, so when you see here is the x-axis is operating pressure, is a bar, is a pressure, and y-axis means is the density. But if you look at the unit here, this is a kilogram per cubic meter, which means it's a volumetric hydrogen storage density, energy density, right? So if you look at the liquid hydrogen at 1 bar, then the volumetric hydrogen storage density is about 70 kilogram per cubic meter. Okay. Actually, if you more pressurize, this can be a little bit increased, but here is it's a 1 bar. It's an assumption is a 1 bar. So we can store 70 kilogram hydrogen in 1 cubic meter. Okay, but let's see the pressurized technology. Ideally, if we pressurize hydrogen under 350 bar, then we can store 28 kilogram per cubic meter. Then if we pressurize this hydrogen to 700 bar, which means it's double pressurized, then we can store, you know, 2 times more hydrogen, right? So 28 times 2, which means we can store 57 kilogram per cubic meter. But this is the case of ideal gas. But if we apply the real gas equation, then it's a different, which means realistically, if we pressure more, but we can't actually store in proportional to this pressure. Okay, let me explain with this. Under 25 degrees Celsius and the 350 bar, then we can store actually not 28, 27 kilogram per cubic meter. Then we double, the pressure will be double. Then we only store 38 kilogram hydrogen per cubic meter. Why is that true? This is because realistically, if you pressurize and more, which means it's the distance between 2 or more hydrogen molecule will be very close. That means it's a repulsion force, then will be very important. So because of the repulsion, you more difficult to pressurize. This is why we can't actually store more and more hydrogen in 1 cubic meter. So if we follow this line, then the theoretical hydrogen storage density is not too much, right? Even if we apply the 1,000 bar of pressure, we only store 50 kilogram per cubic meter. So this is good for a short distance, but not applicable for a long distance hydrogen carrier because it actually provides a very low volumetric hydrogen storage density. That's the problem. So what could then be long distance hydrogen carrier? Why is that so important? Okay, let's see. Let me a little bit talk about this. When you see here is the solar energy distribution globally. So it's a more brown, means it's more solar energy production. But the problem is the geometrical discrepancy for renewable energy production and utilization. Okay, let me explain. If you look at the very plentiful solar energy production site, here is the Middle East, so North Africa, Australia, and Chile, things like that. But this kind of region, there is not many people actually live in this area, which means the energy demand will be about 20 or 30, but the renewable energy production is about 100. So 70 or 80 of renewable energy will be excess. It's surplus, right? But if you look at the Korea here, the yellow, or the Japan and Europe and the United States or Canada, in this area, it's a lot of people actually live in this area, but the renewable energy production is not much, which means is renewable energy production, for example, just renewable energy production is about 50, but energy demand will be 100, which means they need about 50 energy from our outside. Then how we can achieve carbon neutrality globally? So one of the solution for this is surplus renewable energy from here should be transferred, should be delivered into this area, right? So everyone can use renewable energy, so ultimately achieving net zero globally, right? So renewable energy carrier is very, very important. Then what we need to do is, okay, deliver electricity from this and this, and how we can do. That's the problem. So one of the solution for this is we can use battery and store electricity and delivery, but this is not realistic because the battery price is very, very costly, and the battery energy storage capacity is just very small. I'm talking about the thousand, hundred, and thousand terawatt hour scales of energy, but the commercial battery-based energy storage system is just about few megawatt. So we can't actually use battery. Then how we can do? So what can be the renewable energy carrier here? So many scientists actually propose hydrogen as a promising renewable energy carrier, because if you look at this graph here, and what it shows you is a gravimetric energy storage density. So that means it's megajoule per kilogram, means it's 1 kilograms of fuel, how much energy can be stored here. And as you can see here, the hydrogen has a really, really high gravimetric energy storage density compared with the gasoline, diesel, these types of fossil fuel. It's about nearly 3 times higher gravimetric hydrogen storage, energy storage density. And also, hydrogen contains no carbon here. So if you use hydrogen for energy production, the water is the only byproduct. So it's a very, very promising. So the concept will be the renewable energy distribution using renewable energy carrier hydrogen. Then the surplus energy will be transformed into hydrogen, right? Using renewable energy. So transformed into the chemical form of hydrogen. And this CO2-free hydrogen should be delivered into the energy needed area. But the problem is hydrogen is the lightest gas in the universe. So it has really, really low volumetric energy density. As you can see here, the hydrogen, and compare with this liquid types of fuel, the hydrogen gas has really, really low volumetric energy density. That's the problem. But if you're thinking about, deliver fuels, and nowadays, for example, the fossil fuel delivery, actually, we use the very large crude oil carriers, something like this. So we fill liquid fuel here and transport it, right? But if you're thinking about the hydrogen, right? So we fill the hydrogen inside in this limited volume, then the problem, because the hydrogen has a really low volumetric energy density. Then what we need to do is, okay, we need to store hydrogen using liquid hydrogen carrier, and we fill the liquid hydrogen carrier inside these types of VLCC and transport it into a desired site. That's the concept. Then the renewable energy distribution will be the liquid hydrogen carrier. So renewable electricity, surplus renewable electricity will be transformed into hydrogen. Then the hydrogen gas will be transformed into liquid hydrogen carrier, and the liquefied liquid carrier will be transformed into the desired site. That's the concept for achieving global net zero. Then the question is, what could be the liquid hydrogen carrier, right? And what could be the overseas transport hydrogen carrier? What could be the domestic transport hydrogen carrier? Something like this. So the first candidate is okay. Then just, what we can do is, okay, make a liquid hydrogen, right? Gaseous hydrogen has the issue. Then what we can do is, okay, cooling down, the negative 253 degrees Celsius, then we can make a liquid hydrogen. Then the density will be increased, then we can transport this liquid hydrogen into the desired site. So the first is the liquefied hydrogen. So that has high volumetric hydrogen storage density. So 1 cubic meter, you can store 70 kilograms of hydrogen. But the problem is the hydrogen loss. This is called this boil off gas, which means is hydrogen stored temperature is very, very low, right? It's about 20 Kelvin. So even if we make a really, a diabatic and the shield storage tank, but the gas is continuously boiled because of this heat transport. So heat must be in, and the temperature will be, will reach above 20 Kelvin. Then the liquid hydrogen will be boiled, right? So the boiled up gas, then we just lost. That's the one of the issue. And the second issue is, we need high capacity hydrogen liquefaction plants and storage tank and transport ship, things like that. But there are no available this kind of infrastructure at this time, which means is we need to invest significant money for constructing this infrastructure. That's the another thing. But still, nonetheless, this liquefied hydrogen is still one of the promising candidates for long distance hydrogen carrier. The concept here is an overseas and Australia and the Middle East, things like that, so super cheap electricity, and we produce hydrogen from water, which means this hydrogen is called a green hydrogen, or we can use the LNG, the natural gas, and steam reforming process to produce hydrogen and CO2, and we capture CO2 and store. Then this CO2 is not releasing into environment. That this kind of hydrogen is called this blue hydrogen, and this green hydrogen and blue hydrogen called this CO2 free hydrogen. This CO2 free hydrogen and will be transformed into liquid hydrogen at the hydrogen production site. Then the liquid hydrogen will be transported using liquid hydrogen ship into a desired site. And the domestic site, we just increase temperature to make gaseous hydrogen, which is in conjunction with the fuel cell or internal combustion engine to produce electricity and water. That's the concept. And the second candidate for long distance hydrogen carrier is the LOHC. LOHC stands for liquid organic hydrogen carrier. So organic hydrogen. And why we want to use this LOHC? Because the LOHC is a stable liquid at ambient condition. And if you don't use catalyst, then the stored hydrogen won't be released. So you can store hydrogen in a form of liquid organic hydrogen carrier for a long time as a stable state. So that's really good. So you can store hydrogen for a long time. So the LOHC can be used for long-term energy storage. And it has reasonably high volumetric hydrogen storage density. It's about over 45 kilogram hydrogen can be stored in 1 cubic meter, which is smaller than the liquefied hydrogen, right? The liquid hydrogen, the volumetric hydrogen storage density is about 70 kilogram per hydrogen per cubic meter. But in the case of LOHC, it's about 45. And it involves two chemical reactions here. So, for example, the LOHC here, then what we need to do is first the hydrogenation reaction. So then stored hydrogen will be transformed into the LOHC form, into the desired site. And why this LOHC is interesting? Because LOHC is stable, so we can just use the currently existing fossil infrastructure for mass quantities of hydrogen storage and transportation. Okay, the concept the same. The overseas hydrogen produce hydrogen, the CO2-free hydrogen. Then at the hydrogen production site, what we need to do is to convert the hydrogen-rich form of hydrogen, LOHC here. So using a LOHC hydrogenation plant, the hydrogenation reaction proceed to store hydrogen. So that's the liquid, and stored LOHC is a liquid. So because this is a liquid at room temperature and atmospheric pressure, so we can use the currently existing any kind of ship for transportation. And the hydrogen-rich form will be transported into the desired site. And desired site, what we need to do is the second chemical reaction, which is called this dehydrogenation reaction. So using LOHC dehydrogenation plant, here, the hydrogen-rich form of LOHC will be transformed into hydrogen and hydrogen-lean LOHC. And the produced hydrogen will be in conjunction with the fuel cells or turbine to produce electricity. And the hydrogen-lean form of LOHC will be shipped back to hydrogen production site and repeat this process to deliver this hydrogen into here, which means deliver renewable energy into here. Okay? The third candidate for long distance hydrogen carrier is ammonia, which is inorganic hydrogen. So you can use nitrogen as a hydrogen storage media and chemical reaction going on to produce ammonia. Here is the N is missing, it's ammonia. And ammonia is transported into the site, and we can release hydrogen from ammonia for renewable energy we use. Why ammonia is so promising? This is because ammonia has super high gravimetric and volumetric hydrogen storage density. Here, the gravimetric hydrogen storage density is about 17.7 weight%, and the volumetric hydrogen storage density is about 120 kilogram per cubic meter. This is, if you remind the volumetric hydrogen storage density of LOHC is about 45, and some of LOHC has 60 or 70 kilograms of hydrogen per cubic meter, and the liquefaction technology provides about 70 kilogram per cubic meter, and 70 bar compressed hydrogen. The volumetric hydrogen storage density is about 40 kilogram hydrogen per cubic meter. So compare these volumetric hydrogen densities. The ammonia provide much higher. Even, for example, compared with this liquefaction technology, 1.7 times more hydrogen can be stored in the form of ammonia. And the ammonia production, which means it's the reaction of nitrogen gas with hydrogen gas to produce ammonia, that reaction is already commercialized. This is a Haber-Bosch process. So ammonia production, this ammonia hydrogen carrier is readily available. And the transportation is all commercialized. So we can use economical hydrogen storage and transport technology using the currently existing fossil fuel infrastructure. So production is no problem, transport is no problem. The only thing we need to develop is the ammonia dehydrogenation process, which is not commercialized yet. The concept the same, produce CO2-free hydrogen, and at the hydrogen production site, the Haber-Bosch reaction will be proceeded to produce ammonia. Ammonia is readily transported, and at a hydrogen utilization site, the chemically stored ammonia in the the chemically stored hydrogen in the form of ammonia will be released by chemical reaction, and the hydrogen again is in conjunction with fuel cell internal combustion engine to produce electricity, and the nitrogen can be just released into the atmosphere. Right? So that's the things for the long distance hydrogen carrier. And let me switch gear, and the next hydrogen storage materials is the metal hydride. The concept for metal hydride is, for example, the M here, which is metal, and it reacts with hydrogen and nicely stored into MH form, which is again involved chemical bonding formation between the M and H. For example, if we use magnesium, then magnesium react with hydrogen and convert into magnesium hydride. It's a MgH2 bonding, two chemical bondings between the magnesium and hydrogen. So because of this chemical bonding, we called it is a chemical hydrogen storage. And in this way, you can store hydrogen. And here, for example, when made of metal hydride, the volume will be decreased by 1/1500 of room temperature hydrogen gas. So you can make a really compact hydrogen, store the hydrogen here in the limited volume. So in terms of volumetric hydrogen storage density, the metal hydride will be one of the best options. But the problem of this technology here is it has generally low gravimetric hydrogen storage density. Because why is that low? Because compared with the weight of hydrogen, the metal weight is much heavier. So generally, it has low gravimetric hydrogen storage density. And the similar, but a little bit different technology compared with this metal hydride is called this intermetallic hydride. That actually used at least two metals here. For example, the titanium chrome, it has 1.8 gravimetric hydrogen storage density, or the lanthanum nickel alloy, or the lanthanum nickel and some other different metals here, and titanium, iron, and nickel composite alloy, things like that. So generally, many types of intermetallic metal hydride were developed, but generally this most intermetallic metal hydride typically has a very low gravimetric hydrogen storage density. And this is similar, but different metal hydride is the complex hydride. This is a combination of metal and some other inorganic species. For example, the lithium borohydride, right? So sodium is a metal, boron is an inorganic species. These types of metal hydride is called this complex metal hydride. And this complex metal hydride have higher gravimetric hydrogen storage density compared with these types of intermetallic metal hydride, right? For example, the sodium borohydride has hydrogen storage density of 10.6, so which is good. But the problem for this technology is after decomposing these materials to produce hydrogen, and the spent fuel cannot be recovered into this form again with reasonable regeneration energy. That's the problem. So the regeneration is the issue for this complex metal hydride. Okay. Let me then talk about the overseas R&D status for this hydrogen storage. So one of the advanced countries for this concept is actually Japan. Japan consider the liquid hydrogen and ammonia and LOHC as a long distance carrier. Let me first talk about the liquefaction technology between the Japan and Australia. Actually, the Japan and Australia liquid project is going on, shown here. So the concept is in Australia, they use a brown coal to produce hydrogen, so gasification technology to produce hydrogen and CO2, and then CO2 will be stored, and the hydrogen will be cooled down to produce liquid hydrogen. Then the liquefied hydrogen will be transported into this small hydrogen ship into Japan. And in Japan, actually, the hydrogen will be used for hydrogen refueling station and or hydrogen power plant. So that's the plan, and the project is going on. And recently, the Kawasaki Heavy Industry announced that, okay, we're gonna make the liquid hydrogen tanker like this. So that's the ship, but there is no tank up there. So there will be this kind of tank here to deliver liquid hydrogen. So from Australia, again, the brown coal gasification to produce hydrogen and make liquid hydrogen and transporting over 9,000 kilometers to get the liquid hydrogen in Japan, and they're gonna use this Japan. They're gonna use this hydrogen for different applications. And the second examples for long distance carrier in Japan is the Japan-Brunei LOHC demonstration. Japan choose toluene as a LOHC material. So if you see this, toluene has a 3 carbon-carbon double bond. The 1 carbon-carbon double bond can store 1 moles of hydrogen here, and you can store a total 3 hydrogen molecules inside of this toluene by chemical reaction. And through the hydrogenation reaction, then you can transform this toluene into methyl cyclohexane, which is called this MCH. Then the concept is here is okay. Here is the Japan, and here is the Brunei. Then what Japan does is, in a ship they filled toluene here and go to Brunei. And the Brunei produced hydrogen will be stored here by this chemical reaction, right? So toluene react with hydrogen, which is produced at Brunei, and using this hydrogenation plant, they transform this toluene into MCH. This is a liquid, and this is a liquid. Then what they do is this MCH liquid filled here in the first ship here, and they go back to Japan and store here a large hydrogen storage, and on demand, this methyl cyclohexane will be transformed into toluene and hydrogen using this dehydrogenation plant. And the hydrogen will be delivered through the hydrogen pipeline into a hydrogen city, and they consume here, and then reproduce toluene, actually go back to Brunei to repeat this process. Okay, so in this way, actually the Japan get CO2 free hydrogen produced at Brunei, and they deliver into Japan. And when you see here is the Japan, Brunei, this kind of project, and 2020 AHEAD, which is the Japan Association, Advanced Hydrogen Energy Stream Association for Technology Development. The AHEAD actually conducted the world's first hydrogen transport between 2 countries here. And here is the hydrogenation plant with the capacity of 300 cubic meter per hour scale, which is located at Brunei, and they actually proceed this chemical reaction, right? Hydrogenation reaction to produce MCH. Then the MCH was transported, and in Kawasaki City in Japan, using this dehydrogenation plant with the capacity of 300 cubic meter hydrogen per hour, and they release hydrogen from MCH, then the hydrogen was used. So from Brunei, Muara to Japan, Kawasaki City, actually they ideally, but theoretically, they deliver 200 tons of hydrogen annually. So that quantity means is you can refill the 40,000 hydrogen fuel cell car, which is significant. So here you see where the first international hydrogen supply chain was realized between Brunei and Japan. So that was announced by year of 2020. And the third project is the green ammonia project between the Australia and Japan. So they use renewable electricity and produce nitrogen and split water to produce hydrogen, and using Haber-Bosch process to produce ammonia. And the ammonia was shipped into Japan, Singapore, or Korea, things like that. So Australia, actually, they announced Australia national strategy. And one of them is, okay, we're going to produce green ammonia using green hydrogen. And this clean ammonia will be transported into many, many countries. Again, currently the ammonia sea transport is readily available, and the land transport is also readily commercialized and available. So there is no problem, except the ammonia dehydrogenation. So based on these technologies, I mean the long distance hydrogen carrier, the Japan government constructed the international hydrogen supply chain to secure the hydrogen supply for Japan. Actually here, from Brunei, the hydrogen will be transported in the form of a LOHC, and liquid hydrogen or ammonia will be transported from Australia into Japan. The Middle East, they produce ammonia, which will be transported into Japan in the form of ammonia from Chile, using Chile wind power to produce green hydrogen, and over 18,000 kilometer transportation to deliver into Japan and Canada and United States. The hydraulic power to produce green hydrogen will be transported into Japan, things like that. So the Korea government also constructed this international hydrogen supply chain based on LOHC and liquid hydrogen and ammonia. Okay. Germany, actually, they also, conduct relevant R&D for the LOHC here. The one of the company here in Germany, Hydrogenious Technology, actually they choose dibenzyl toluene as a potential LOHC, which is, the dibenzyl toluene is a toluene backbone, and these two benzyl group is randomly connected, because this dibenzyl toluene has 9 carbon-carbon double bond. We can store 9 molecules here to produce hydrodibenzyl toluene. And as you can see here, this company, developed the hydrogenation and dehydrogenation plant, small module for different application. And this is one of the example for LOHC dehydrogenation module here, the hydrogen leach LOHC here, and they passing through this reactor, which is equipped with the relevant catalyst, and they decompose this hydrogen-rich LOHC to produce hydrogen, and hydrogen lean form of LOHC, and the hydrogen will be used for different applications. And based on this hydrogenous technology in Germany, if we use their LOHC and we shipped this LOHC in the volume of 75,000 cubic meter of this LOHC tanker, which means is you deliver 3,400 tons of hydrogen in one time. So that amount means is you can refill 680,000 hydrogen fuel cell electric vehicle, or nearly 136,000 of hydrogen bus, things like that. So which is, readily available and promising. And some of motor car company actually develop LOHC-based hydrogen vehicle, because nowadays hydrogen fuel cell vehicle use the 700 bar pressurized gas tank. There are some safety issues here. So because of these safety issues, these companies want to develop new technologies using LOHC here. And one of the issues for LOHC is the dehydrogenation actually require a lot of energy. That's the problem. So to decrease the dehydrogenation energy, what some scientists actually did is to introduction of this heteroatom here. So for example, this ring, the the 6 carbons ring here, if you add the nitrogen and the dehydrogenation enthalpy decrease, so the dehydrogenation temperature can be decreased. And if you introduce 2 heteroatoms here in the ring, and the more, the temperature is more decrease and more decrease and more decrease. So using this concept, the Air Product company in the United States actually developed new types of LOHC, which is called this N-ethyl carbazole, the 3 rings here, and in the center ring, they introduce a nitrogen atom here. So in this way, actually, when you hydrogenation, when you store hydrogen, then the stored hydrogen releases the endothermic reaction, and the endothermic reaction enthalpy can be decreased into 50 kilojoule per mole hydrogen. In the case of toluene, for example, so we made MCH, and MCH dehydrogenation require the reaction enthalpy of it is about 75 kilojoule per mole, 68 kilojoule per moles of hydrogen. So compare to this MCH, this hydrogen-rich ethyl carbazole has much lower reaction enthalpies for LOHC dehydrogenation. And another example is ethyl indole. So two rings and 1 nitrogen atoms in it. And Wuhan University actually used this LOHC to drive this hydrogen bus. And in the United States, the ammonia R&D is going on for here, using renewable energy to produce ammonia electrochemically, and the ammonia stored and transported, and the ammonia decomposition. This is a thermal decomposition way to produce hydrogen, which means it's energy recovery, and to achieve these total cycles based on ammonia, and they want to use ammonia as a hydrogen carrier. And if you look at this map, actually the United States has already ammonia transport infrastructure shown here. So from Louisiana to Minnesota and the Indiana to Nebraska. So there is a solid ammonia transport infrastructure. So you can take ammonia on demand to decompose to produce hydrogen. The Australia developed hydrogen separation membrane. So upon ammonia decomposition, they produce ammonia, hydrogen, and unreacted ammonia. And using this membrane, only hydrogen was separated, and we can produce high purity hydrogen for several applications. So what they did is, CSIRO is a kind of government-funded lab like KISS, and actually they recently developed this technology and apply for refueling this Nexo fuel cell electric vehicle successfully. And I'm gonna just skip here. So actually, Postec used this, the similar strategy for chemical hydrogen storage. Actually, we use small molecules here and react with hydrogen to produce relevant hydrogen energy carrier, and then it delivered and on demand, and we proceed the dehydrogenation reaction to produce hydrogen, and we use this renewable energy release. So mostly I use small molecules here. For example, if you use oxygen molecule here, the hydrogen energy carrier can be hydrogen peroxide. If you use nitrogen molecules here, the hydrogen energy carrier can be ammonia. And we can use also CO2 here. Then the hydrogen energy carrier could be methanol and the methane. Methane is a gas, methanol is a liquid, or the formic acid is also a liquid. And I also use LOHC here to produce LOHC, the hydrogen stored LOHC. And very firstly, actually I use the boron and nitrogen containing molecules here to produce ammonia, borane, and sodium borohydride as a hydrogen carrier. So let me just briefly introduce my research here. First, it's a formic acid. This is CO2-based hydrogen storage material. Why I'm interested in formic acid as a hydrogen carrier is it is relatively non-toxic and stable liquid at room temperature. The formic acid grammatical hydrogen storage density is a little bit low. It's about 4.48%, but it has reasonably high volumetric hydrogen storage density of 53 kilogram per cubic meter. Again, 700 bar hydrogen storage pressurized hydrogen has about 40 kilogram hydrogen per cubic meter. So this formic acid is a little bit higher volumetric hydrogen storage density compared with this pressurized technology. And the dehydrogenation can be readily achieved even at room temperature. So if you develop relevant catalysts for dehydrogenation, we can release even at room temperature. This is one of the key advantages. So what we want to do is to develop really good catalysts to activate this CH bond and activate this OH bond. Then recombination this H and H to produce H2 and CO2 as a medium, right? That's what we want to do. But our catalyst can also proceed this CH bond activation as well as the CO bond activation. Then we're going to produce water, right? Water and carbon monoxide here. The problem is if we produce carbon monoxide, then we can't actually use this gas for fuel cell application. Remind that PEMFC, the PEM fuel cell, actually they use platinum catalyst as an electrode material. And if CO exists, then CO poison this platinum catalyst to deactivate whole fuel cell system. So that's the problem. So what we actually really need for catalyst development is to develop highly selective and stable and highly capable catalysts to proceed only these dehydrogenation reactions. So actually, previously I used palladium as an active site and nitrogen containing support for this purpose. So this, I used the carbon nitride. So it's a carbon nitride material. So it's aromatic conjugated and graphite-like 2D structure. And there are a lot of nitrogen atoms here. So probably the nitrogen site play a dual roles as Lewis basic site for palladium, which means is, if you see the HOMO structure of this material, electron field site exists here. So the palladium actually interact with this nitrogen, then the electrons will be, transported into palladium site, which makes palladium site electron rich, then facilitate our targeted formic acid dehydrogenation. And the second role of this nitrogen site is that site can also play as a Bronsted basic site. So the first of the, to dehydrogenate hydrogen from formic acid, the first step is this deprotonation. So this nitrogen site can help deprotonate this proton from formic acid. This is what I thought. So we actually developed a nano catalyst based on this concept and produced the palladium supported on carbon nitride. And what we, as you can see here, the compare with the palladium supported on carbon, our developed catalyst shows much higher reactivity. The support itself shows no reactivity for formic acid dehydrogenation. And the similar concept, I used nitrogen doped carbon species or the amine functionalized the SBA15, so major for silica. The silica materials, I make some amine functionalized ligand here that interact with the palladium nanoparticle size to show the similar effect for them. And formic acid dehydrogenation, many scientists actually develop a catalyst for formic acid dehydrogenation, but the CO2 hydrogenation is not really significantly studied, compared with this formic acid dehydrogenation. So one of the reasons for this is tough, more difficult. So which means is formic acid dehydrogenation has no problem, but CO2 hydrogenation is tough. Then the question is, how about, what are other chemical hydrides that have increased reversibility? To resolve this issue, actually, I switch into liquid organic hydrogen carrier with a pi conjugated ring. Actually, the formic acid is also the one of the LOHC, right? So liquid organic hydrogen carrier, but I decided to use LOHC with the pi conjugated ring for reversible liquid carrier. So what I actually use is these types of biphenyl species. The carbazole, actually the US Air Product Company actually developed these species. And I choose actually this biphenyl-based LOHC for potential LOHC candidate. One of the reasons for this is if you see the gravimetric hydrogen storage density, these biphenyl types of species has much higher gravimetric hydrogen storage density compared with this carbazole or other stuffs. But the problem is the biphenyl itself is a solid, right? This is not liquid, it's a solid. The melting point of this biphenyl is 70 degrees Celsius, which means it's solid at room temperature. So our strategy is, okay, this is, really it has high gravimetric hydrogen 3 density. So I want to actually still use this bipanel. Then how we can do to resolve this issue? So one of the solution, and what we did is actually, okay, then we can co-use this other species to make eutectic mixture, which means is, okay, we actually choose here dipenylmethane. The difference between these two molecules is this, the ring is directly connected, and here is the bridge, CH2 bridge here. Because of that CH2 bridge, the gravimetric energy hydrogen 3 density is a little bit decreased, but the melting point is much low compared with this. So what we did is actually we mixed this together with a specific ratio, then it turns to liquid at room temperature. This is called this eutectic mixture. Then this eutectic mixture, when we use the ruthenium alumina catalyst at 150 degrees Celsius under 50 bar of hydrogenation reaction is completely nicely completed. It's a very easy reaction and clean. So all this hydrogen was actually stored in the forms of this molecule. The hydrogen-rich LHC is liquid, which is good. And the problem for here, not only for this material, for LOHC, the issue is again the dehydrogenation reaction, because dehydrogenation reaction is endothermic reaction. So if you look at this equilibrium conversion, right? The x-axis is temperature and the y-axis is a conversion. Under 500 kelvins of reaction temperature, the major form will be the hydrogen-rich form, right? To release hydrogen from this molecule, for example, 99.99% conversion, that means it's existing this form. To exist this form, actually we need nearly over 300 degrees Celsius of temperature. Then this form is stable compared with this. That means for dehydrogenation reaction, definitely we need over 300 degrees Celsius, which means is the delta H reaction enthalpy for dehydrogenation will be 62 to 65 kilojoule per moles of hydrogen. So that's the problem. So you require energy and require higher temperature. But that doesn't necessarily mean is the dehydrogenation doesn't go. Actually, it goes. Dehydrogenation can proceed in the presence of an appropriate catalyst. So when we develop platinum-based catalyst and we proceed at 300 degrees Celsius on the 1 bar of reaction, it go for hydrogen releasing reaction to produce this bag, this LHC bag with the hydrogen. So this eutectic mixture can proceed hydrogenation and dehydrogenation reaction reversibly. So you can store hydrogen and you can release hydrogen. And based on these materials, we developed the reactor here, shown here. It's this dehydrogenation reactor scale is about 1.25 kilograms of hydrogen per day. And based on this data, we scale up here. And this is a 5 kilogram hydrogen production dehydrogenation reactor per day. So we successfully demonstrate these LHC materials and dehydrogenation reactor. And other liquid energy carrier, now I'm considering methanol as a fuel. And the concept is the CO2 mediated. And the CO2 will be reacted with 3 molecules of green hydrogen to produce green methanol. And we can use methanol, and when we on demand, we can decompose the methanol to produce hydrogen back. But that's what we are doing right now. So we are developing relevant catalysts for this reaction. Inorganic carrier, I previously used ammonia borane, this kind of thing. And the ammonia borane structure is the BH3 and the NH3 here. So if you consider the electrons here, two electrons, it's a lone pair electron actually donating into this boron to make a stable structure. So one of the interesting characteristics of this ammonia borane is this H is hydridic, partially negatively charged, and this H connecting to nitrogen atom is protonic, which means it's partially positively charged. And this reaction, this ammonia borane can produce up to 3 molecules of hydrogen, which means its hydrogen storage density will be 19.63% theoretically. So this is even the gravimetric hydrogen storage density is even higher than ammonia. So this is good. So US Department of Energy actually consider this ammonia borane as a transportation fuel for fuel cell electric vehicle. But if you look at the ethane molecules here, right? Ethane and ammonia borane is an isoelectronic structure. The molecular weight the same. But in general, scientists, think, two molecules has an isoelectronic structure and physical property may be similar. But in this case, it's hugely different. The ethane molecule, the melting point is a negative 182 degrees Celsius. But ammonia borane is a melting point is about over 100 degrees Celsius. It's definitely solid and room temperature. But this is definitely a gas state at room temperature. The melting point temperature difference is so 200 degrees Celsius. That's the problem. That's not the problem. That's the interesting part. So
why is that so different between these two?
Characterize the solid state structure of ammonia borane, and it turns out this BH again is a hydridic, and this is NH is protonic. And in the solid state structure, scientists found that there are many interactions between this BH and NH. This is called this dihydrogen bonding interaction. And because of these interactions, this molecule is stabilized and exists as a solid at room temperature. And so what might be happening for upon hydrogen release? So, scientists found that upon heating of this ammonia borane, this NH and BH can interact with each other to produce hydrogen and make these types of BNBN polymer. That's what scientists actually found. And ammonia borane, if you heat ammonia borane at 85 degrees Celsius and it doesn't release hydrogen, and upon increasing reaction temperature at 90 degrees Celsius, about until 30 minutes, there's no hydrogen production, and then slowly releasing hydrogen. And if you increase the reaction temperature to 95 degrees Celsius, then induction period is shortened. So 10 minutes, there's no reaction in 10 minutes, then release hydrogen. And if you increase the reaction temperature higher and higher, the induction period is continuously shortened. So the question is that what's the role? What happened in this induction period? So what might be happening, right? So people start to think about it. Then the hint will be, maybe under induction period, this kind of dihydrogen bonding in the interaction will be perturbated. And, this interaction is perturbated and broken and melting and reaction happen. This is what actually scientists characterize. And my lab actually used metal-free catalyst to promote hydrogen release from ammonia borane shown here. What we found is that we use this oxygen-containing chemical, then it produced it. There's what we found is that we shorten the induction period, we absent the induction period and release hydrogen. And I'm not really talking about the details for the mechanism, but what we found is that these types of chemical can interact with the ammonia site and produce electron density, providing electron density to make this terminal BH more hydrated. And this more hydrated BH can interact with each other to make this DAD species, then proceed hydrogens. Okay, so based on this ammonia borane and our developed metal-free catalyst, we designed the reactor shown here. So ammonia borane is a solid, so we make ammonia borane bead and take ammonia borane bead conveyor, the ammonia borane delivered into the reactor, and reaction goes and produce hydrogen. The hydrogen was actually delivered into, okay, okay, just let me have a quick break. 예, 예, 지금 제가 회의 중이라서요. Okay, sorry for this, and the movie is not actually working, and the produced hydrogen was actually connected with into a drone for flight. This work is in collaboration with the Aerospace Research Institute. And another inorganic hydrogen carrier is the hydrogen. The hydrogen, upon decomposing hydrogen, and it produces nitrogen and hydrogen. So we can use this hydrogen. And ammonia is the, I said, the most representative hydrogen inorganic carrier. And there are commercial ammonia synthesis Haber-Bosch process and other achievement actually give 3 Nobel Prize here. So here the Haber Nobel Prize in Chemistry 1918, Bosch Nobel Prize in Chemistry in recognition of their contribution to the invention and development of chemical process is actually the chemical high pressure method. So this is called the Haber-Bosch process. And the 3rd Nobel Prize came from the achievement for these scientists and studies of chemical processes on solid surfaces. It's a mechanistic study revealing catalytic mechanism of Haber-Bosch process. So this is the commercial Haber-Bosch process reactor. So now the hydrogen actually comes from this natural gas, but in the future, the hydrogen will be should be from water. So nowadays, steam reforming process to produce nitrogen and hydrogen that go for water gas shift reactor and Haber-Bosch reactor to produce hydrogen. Okay. My computer is slow. Okay, so this is commercial ammonia synthesis process. This is KBR company has a license for this chemical plant for ammonia synthesis. And this is a process I'm not going to talk about it. And ammonia dehydrogenation is the key for achieving ammonia-based cycle, but not commercialized and no commercial ammonia dehydrogenation process available today. So our lab actually developed many for ammonia dehydrogenation reaction, as you can see here. Mostly the active site is ruthenium, and we varied the support, the lanthanum doped alumina, and some sort of zeolite species, nitrogen doped carbon, and silica-based material. This kind of thing. And this catalyst was actually we conducted technology transfer based on this catalyst to a free company, and based on our catalyst and concept, we make these types of small ammonia-based power pack shown here, and that's the reactor, and that's the ammonia tank. So upon supplying ammonia, and ammonia was composed inside of the reactor and produce hydrogen, and hydrogen was delivered into the fuel cells to give electricity, which is then supplies to this drone. And the Hyundai Motors asked me to scale up our concept. So we make these types of reactor, and the ruthenium catalyst actually equipped inside, and ammonia going passing through this reactor to produce hydrogen. And that's the thing. And the dimension is not really big, it's 25, 100 centimeters of dimension, and it continuously produces hydrogen, which is good and which can be used for different application. And we actually reported this world first for this ammonia dehydrogenation efficiency, system efficiency, and system efficiency will be about 84%, and continuously produce hydrogen, which was then connected into a fuel cell to give 5 kilowatt of power. Yes, this is a kind of summary. This is summary, final summary. So we did small molecule-based hydrogen, chemical hydrogen storage. For the first time, I used ammonia borane. Then, I was talking about the formic acid and some sort of methyl and the LOHC from here to there, from here to LOHC. This is because I want to make more reversible liquid hydrogen carrier. And nowadays, I'm also focusing on ammonia because ammonia provides much higher hydrogen storage capacity. And in the future, I'm gonna develop new materials and the materials related catalysts and system. That's my R&D status. Okay. So over here, yeah, that's the last slide, and this is the kind of summarize for chemical hydrogen storage, and which was provided by the U.S. Department of Energy. And the x-axis is the hydrogen storage temperature, and y-axis is the gravimetric hydrogen storage capacity. And here, the liquid nitrogen temperature. I was a little bit talking about the adsorption-based hydrogen storage, which is called the MAP, metal organic framework, and the metal hydride or complex hydride, intermetallic hydride. The operation temperature is about 300 degrees Celsius, right? Yeah, this is a metal hydride. And some of the ammonia borane, actually, their operation temperature is room between the room and 100 degrees Celsius. So because of that reason, and a region of high electric energy, because of that reason, the U.S. Department of Energy considered this ammonia borane as a transportation fuel. But nowadays, they decided that the ammonia borane is not, it's not going to be used for transportation fuel because the regeneration process is energy intensive process. Okay, but this many actually people research it, and the LOHC actually working something like here. Okay, that's it, and that's what I prepared. And thank you very much for your attention.
Thank you, Professor Yun, for the lecture. Unfortunately the last 3 minutes there's some things wrong with the connection, so sometimes it's lagging up, your voice is lagging up, so but it's just like the last 3 or 5 minutes.
Okay. All right, sorry for that.
It's okay, Professor. So class, do you have any question for Professor Yun? So as we see the lecture from Professor Yun, this technology is we can say it's like an advanced technology, right, Professor? Because nowadays all the Japan, Korea, America, they're using this kind of technology for the alternative energy, right, Professor? So it's not an old technology, it's like advanced technology for the alternative energy, right, Professor? So it's not an old technology, it's like
I'm sorry, I didn't hear that.
Okay.
The connection problem, maybe. Yeah.
Yeah, Professor. Okay, we have this 3 from Syntesa. Maybe you can ask Professor Yun directly about the lecture. So Yun about the lecture.
Okay. Okay, Mr. Ridwan. Is my sound clear right now?
Yes.
Okay. So
Can you open the video?
okay, I'm sorry. I'm really unfortunately I'm not available for turning on my video.
Okay.
Okay. First and foremost, I would like to introduce myself. So my name is Syntesa Alvan. You can simply call me Sin as well, Professor Yun. And thank you for this great opportunity. Good morning, Professor Yun and Mr. Ridwan. And before I jump into my questions, I would like to say thank you for this interesting and important lecture here. So my question is, as shown in the previous diagram, to be precise in the early slide, that the captured hydrogen can be used as a fuel cell for some types of utilization, right? Such as power plants or electric power generation, or even on home scale. So I want to be specific on home scale utilization. So is there any other possible place to put the hydrogen tank except in the car? For example, is it possible for us to place it underground? Because I think it would be way easier for us to utilize the captured hydrogen, especially for the home scale utilization. Or
home scale utilization.
Yes.
So I think it's, or the car itself has provided like the required conditions for the optimal captured hydrogen. Thank you. I'm sorry if there is a potential for misunderstanding here. Thank you very much. Your question is, what's the other home scale application for hydrogen?
Right. For a home scale utilization, is there is possible place for us to place the hydrogen tank underground, except in the car, like you have explained before, I think. I'm sorry if there is a potential for misunderstanding here. Thank you.
No problem. Very good questions. And yeah, definitely there is a possibility to store hydrogen underground. It's not the that for a car. Actually, some people actually use that underground hydrogen storage. For example, this is compressed. They actually to store mass quantities of hydrogen underground. What people actually use right now is to make it's a salt cavern. It's some specific rock cavern. Then we actually store high pressurized hydrogen in the cavern.
I
And
see. Okay.
On demand, we produce the compressed hydrogen outside in conjunction with turbines, some things like that, to produce power. That's the one of things for really mass quantities of energy stored in the form of hydrogen. That's the one thing. And for home scale application with hydrogen, I think one of my vision is as time goes by, probably the needs for robot, the application, right? There should be increasing for robot application, because we are getting older, and many robots actually can help the human's life. Then what we need to do is how we can power the robot. One of the easiest thing to think to power the robot is we can use the battery, right? But the battery is not may be good, but may not be good for continuous application for this kind of robot. For example, in the drone application, when nowadays mostly we use battery to power the drone, but the only application time is less than 20 minutes, because the gravimetric energy storage density of a battery is not very high. But hydrogen can be used for this application, and especially the liquid types of hydrogen storage materials can be used. For example, formic acid can be used for that to power the robot, or maybe methanol. Methanol is toxic, then we can use ethanol. We can use ethanol as a hydrogen carrier, and we use that fuel for powering robot. So that's I think that's one of the application that for home scale hydrogen.
Okay. Thank you, Professor Yun. It is quite easy for me to be understood from your answer. I think that's all, Professor Mr. Ridwan. Thank you.
Thanks.
Okay. Thank you, Sintesa, for the question. So now next question is from Farah Marcela. Time is yours, Farah.
Okay. Thank you, Dr. Yun, for the interesting lecture today. So I have two questions about the hydrogen carrier. For the first question is, what important things should be in a hydrogen carrier ship? And for the second question is, there are some countries that are still in the process of developing hydrogen carriers, such as Japan, Korea, and Brunei. What problems did they encounter so that there's something that needs to be developed, or what things that they want to improve? Thank you, Dr. Yun.
Okay.
Okay. I'm sorry. Yeah, sound. Yeah.
Is it not clear right now?
Yeah, I didn't hear that. Sorry.
Okay, so I have two questions about hydrogen carrier. So for the first question, what important things that should be in a hydrogen carrier ship? And for the second question, there are some countries that are still in the process of developing hydrogen carriers, such as Japan, Korea, and Brunei. what problems did they encounter so that there's something that needs to be developed, or what things that they want to improve so that in that development.
Oh, okay, okay. So now the connection problem sometimes is still my computer is has some issue. For the hydrogen carrier ship, you mean the first question is the hydrogen carrier ship? There is a issue for that, or the so your first question is the is there any some of the issue or the important things for hydrogen carrier ship?
Yes, that's it.
Okay.
So the main things that is should be in a hydrogen carrier ship.
Yeah, for ammonia carrier or the LOHC carrier ship, there is no problem. So we can just use it based on the current technology. But in the case of liquefied hydrogen, liquid hydrogen, then there will be a lot of issues that need to be resolved. For example, do you remember the boil off gas, things like that? So when we carry the really large quantities of liquid hydrogen, it continuously release the gaseous hydrogen. That's the problem. So what we need to do is how we can use the boiled off gas. For example, we ship the liquid hydrogen from Australia, and to reach the 100 molecules of hydrogen is shipped from Australia as the liquid hydrogen, and it lose 100 and 90, 10, we lost 10, 90, 85, something like that. And how many molecules can we use in Korea, for example, after 2 week or 3 week shipping? How many molecules we're gonna lose? That's the problem. So one of the idea for this is we can use boil off gas. The boil off gas can be supplied into the ship propeller. I mean the combustion engine for driving the ship. So that's the one thing. Yeah, and how we can thermally well insulate it. That's the one of the other thing. And you can imagine really big gas liquid hydrogen tank, and then what types of materials we need to use, right? And how we can insulate this kind of really big surface, I mean the tank surface area and volume ratio, how we can adjust this surface area and volume ratio, things like that. That's the one of important consideration to develop the liquid hydrogen carrier ship. Okay. And the second question is, so there is a kind of intercontinental or the really good international hydrogen supply chain projects are going on between Japan, Brunei, or Korea, Brunei, things like that. And your question is, can you repeat your question for that? The second question?
Yes, of course. So the things that I want to ask is, what problems did they encounter so that there is something that needs to be developed, or like maybe that there are things that they want to improve?
For example, the ammonia, in the case of ammonia, there is no problem. So for example, in Korea, we import ammonia. We import 100% ammonia right now. So we just import, but what we need to do is to develop ammonia dehydrogenation technology. This is what we need. And for LOHC, between two countries, there are no problem, right? So we need hydrogen. So what we need to do is we need to find relevant countries for hydrogen production. but the technology itself, and for LOHC, we need to develop hydrogen LOHC, hydrogen storage plant, and LOHC, hydrogen dehydration plant. But for hydrogenation plant, there's no problem. This is all, many oil company actually, they use a really big size hydrogenation plants. So probably there's no problem. But LOHC dehydrogenation, that probably we need to develop, especially for separation and purification technology will be important, because the LOHC dehydration involve really high temperature, right? So over 300 degrees Celsius temperature for a long time, chemical reaction. Then what, our hope is just only produce hydrogen without the decomposition of LOHC itself. But the problem is the really high temperature for long time operation. Then the problem is the LOHC can be decomposed. Then the output gases will be the hydrogen and the decomposition species and some unreacted LOHC, hydrogen-rich LOHC, things like that, right? Then how we can purify and how we can separate the high purity hydrogen. That's the one thing we need to develop. And for liquid hydrogen, for example, for liquid hydrogen, there are many issues for that, except not only for liquid hydrogen carrier ship development. There is no ship available, commercially available for liquid hydrogen carrier ship. There's no ships here, so we need to develop. And all the port structure should be constructed. So that actually require mass investment for that. So that's the problem. Actually, not technically. It's more economical point of view. There are some issues for liquid hydrogen. Okay. Yeah. All these are answered to you properly?
Yeah, it probably answers my questions. Thank you very much, Dr. Yun, for the explanation.
Thank you very much for your questions.
Thank you, Professor Yun. So we have one more question, Professor, from Nabila Bisansa. Go ahead.
Okay, thank you, Mr. Ridwan, for the chance, and thank you for your insightful explanation, Professor Yun. My name is Nabila Bisansa Putri, and I'm a student of Mr. Ridwan class. I'm sorry if you have discussed about this before, but I still don't get it about which method of hydrogen storage method is the best among metal hydride, intermetallic hydride, and complex metal hydride storage.
Okay.
Could you please explain a little
I'm sorry. The sound is. Yeah, sound is. Yeah, I didn't hear that.
Yeah.
Sound is.
Yes. Can you repeat that one, Nabila?
Sorry, my connection maybe is unstable.
I have a problem. I didn't hear that. No
Yes,
sound.
we didn't hear also, Professor. So maybe his connection also has a problem. Her connection.
Yeah.
Yes, Nabila.
I still don't get it about which
No
method.
sound. Sorry.
Oh.
So
Yes, sounds like
yeah,
don't
some
get it.
problem.
Yeah, sounds like that.
For the connection.
So there should
Yes.
be the connection. Yeah.
So maybe I would like to give a note that what Nabila trying to ask is compared with other kind of hydrogen storage, sometime like metallic. Okay, we have a chat for this one. Thank
Okay.
you for the chance and thank you for your insightful explanation, Professor Yun. My name is Nabila Bisan Saputri and
Nice
I'm a
to meet you,
student of
Nabila.
Mr.
Yeah.
Ridwan's class.
Okay.
Yes, I am sorry if you have discussed about this before, but I still don't get it about which method of hydrogen storage is best among metal hydride,
Okay.
intermetallic hydride, and complex metal hydride storage. So between these three, metal hydride, intermetallic hydride, and complex metal hydride, which one is better, Professor?
Okay. Okay. So do you hear my voice?
Yes, now
Okay.
we can hear your
Okay. Okay.
voice.
Okay. Yeah, that's good questions. And thank you very much. Thank you very much for your questions. And for the metal hydride, okay. Let me first talking about metal hydride is not considered as long distance hydrogen carrier. Okay. Nonetheless, metal hydride based storage is a very good, one of the very good option for different application. So mostly intermetallic hydride again has a very low gravimetric hydrogen density, so which was not really significantly researched nowadays. And complex metal hydride and sodium borohydride, for example, has been extensively studied, and actually they applied for powering hydrogen car actually, and they make a small power packs for producing electricity based on fuel cell. There are a lot of examples. So sodium borohydride and this kind of magnesium borohydride, sodium borohydride, these kind of things are really, really good options to make a portable device in conjunction with the fuel cell. And metal hydride is also a good option, especially the magnesium hydride based hydrogen storage tank is now being used for submarine technology. In the submarine, and they actually use the magnesium hydride. They use the magnesium hydride tank to store hydrogen, and on demand they heating up and releasing hydrogen, which is in conjunction with the fuel cells to power the submarine. This is German HDB company actually use this technology for one of the advantages for this metal, especially metal hydride application is it is really, the hydrogen storage and release is really, really reversible and reproducible and reliable. So for military purposes, the reliability is very important. So in this purpose, the metal hydride is one of the really good option, even if the storage cost is expensive, but it's the reliability and reproducibility makes metal hydride for different applications, especially for military applications. Okay.
Okay, Nabila, is that answered
Is that
the
answer?
question?
Yes. Thank you so much, Professor.
Thank you.
Okay, thank you, Nabila, for the question. So
Okay,
the time is
Professor.
9:55, Professor.
Yeah. So Professor, I need to go.
Yes, that's how
Yeah, it's
you
about.
need to check out from the hotel, right?
Yeah.
So before that, I would like to maybe just one briefly thank you. I would like to have send you gratitude for having this collaboration for this lecture series, professors. We would like to give thanks to you. And then actually we have this kind of certificate for something like certificate for you because you already certificate of appreciation. I'm sorry. So, but can Mbak Safira, can you open the share the kind of certificate for this one, and I will send you through email this this professor.
Okay.
And thank you. On behalf of this head of department, Professor, I'm sorry he's not able to join us in this lecture. We would like to say thank you for this lecture series. Hopefully, you can join us another kind of program for the special lecture, Professor. If
Yeah,
you don't mind.
I would love to.
Yes.
Okay.
Thank you very much.
Thank
So,
you very much.
I will see you soon, probably. I will chat you from Katok for other kind of
Okay.
talk. Yes. Thank you very much, Professor Yun. See you next time. Have a great day, Professor.
Thank you. Thank you very much all and have a great day. Thank you so much.
Thank you, Professor. Bye.
Bye.
Oke, terima kasih buat teman-teman kelas KSKF. Jadi ini terakhir ya, sesi terakhir dari kuliah Profesor Yun. Selanjutnya mungkin akan saya berikan sisa-sisa dari perkuliahan yang ada. Jadi kita masih belum membicarakan tentang teknologi fuel cell secara detail gitu kan ya. Nanti mungkin kebetulan minggu depan saya ada jadwal ke Korea, jadi mungkin perkuliahannya juga online juga ya. Jadi tapi minggu depannya lagi mungkin offline. Tapi nanti saya informasikan lebih lanjut. Sampai sini ada pertanyaan mengenai perkuliahan?
Belum ada Pak dari saya Pak.
Oke, siap. Terima kasih. Tadi saya lupa karena Profesor Yun tadi buru-buru karena kemarin dia bilang dia harus check out-nya sebenarnya jam 11, tetapi mudah-mudahan dia bilang boleh check out dari hotel. Takutnya dia kena denda kan ya kalau misalkan di atas jam 11 karena sekarang di sana jam 12 berarti. Makanya tadi dia buru-buru. Jadi lupa foto-foto kita jadinya. Oke, saya tutup. Terima kasih atas kehadirannya, atas partisipasinya. Dan lagi tadi yang bertanya Farah, Sintesa, sama Nabila, yang seperti biasa kan saya sudah ada voucher 50.000, 50.000 aja sih, tapi lumayan lah untuk setiap penanya yang ada di kuliah Profesor Yun. Jadi saya hari ini sampai jam 10.30 ada di meja. Jadi kalau mau ambil silakan datang ya, nggak usah malu-malu. Mario juga udah ada 2 kali pertanyaan tuh, jadi lumayan cepet bagi-bagi sama teman-temannya.
Baik Pak.
Sip. Saya tutup. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Pak.
Terima kasih Pak.
Oh jangan lupa absen
Terima
pulang
kasih, Pak.
yang sudah ada di chat ya. Tolong absen pulangnya ya. Oke.
Terima kasih Pak.